Morning, everyone. So we're going to continue our final review into acid bases. This is Unit 4 of our course. We started off this chapter, we broke this up into two parts. So this is a fairly long chapter. Hopefully this overview can do it all in one lesson here. So first thing for starters here was a few basic definitions. We started with what's referred to as the Arrhenius definition. They will very commonly, for a multiple choice question, ask you what's the definition for Arrhenius acid or Arrhenius base. Although for most of this chapter we had worked more with this Bronsted-Lowry definition, you still need to know the basic definition. So the Arrhenius definition is typically the one that we know. Acids are chemical. They don't just have an H. It's going to be H something. But the thing is, when you actually drop them in water, they actually have to be able to release this H plus in water. Right? So acids, their job is to release H plus in solution, which is why we said, well, you have to have a football to give or else you can't lose the H plus. In a similar fashion here, Arrhenius base, it's going to release the characteristic base molecule, which is hydroxide, which is why we've been saying, okay, well, it's going to be something with OH, sodium hydroxide, lithium hydroxide, whatnot, okay? Those ones there, that one there, likewise, it has to be able to release an OH minus when dropped into water, when dropped into solution, right? There are many chemicals that are neither acidic nor basic, okay? I know acids and bases are sort of opposite of each other. In general, other ionic compounds are just referred to as salts. Salts are just ionic compounds that don't release the H plus nor release the OH. Because acids and bases, they neutralize each other here. It essentially is like a special case of a double placement equation where your acid, it's HA, we're going to react it with so far BOH. They're going to basically switch partners here. We're going to end up forming a salt. That salt here is not always going to be table salt. It's just going to be some generic ionic compound. And then basically it's the H from the acid. By switching places with the B here, it ends up forming HOH. And therefore we know HOH is actually water. If you look at the net ionic equation for these ones here, it is just going to be the acid's job is to donate the H plus in a 1-to-1 ratio with hydroxide in forming 1 water. Just case in point here, for the first little bit, we've been mainly focusing on just strong acids and strong bases. So if this is a strong, we know it's a one-way arrow and ends up forming H plus and A minus. Similarly, BOH here, even though this wasn't on our table, we said any soluble salt that breaks up to become B plus and OH minus like this, because they break up 100%, our net is basically an acid gave an H plus and the base gave OH minus that can then neutralize. What if I tried to ask you, what is the net ionic equation if I reacted CHQ, so our weak acid, acetic acid, let's react this with NaOH. Now we know sort of at the heart of it, the job of the acid is to donate the proton. The only problem here is the CHQ is actually a weak acid. In fact, we learned later on in this chapter when we looked at Ka constants, things like that, we found that if we were a weak acid, the equilibrium constant heavily favors the reactant side. So if I were to do a net ionic equation for this expression here, we've seen weak acids and strong base titrations with titration curves, things like that, I wouldn't just break off acetic acid to become H plus because I know the majority is still acetic acid. But for the little bit of H plus that actually does manage to break off, it's going to react. The sodium hydroxide is a one-way arrow, so I'm just going to say OH minus, and then basically we're going to end up forming our acetate ion, we end up forming our conjugate base, and then we end up forming water there. So we still need to do the balancing for mole ratios, things like that, but just in case for trying to write a net ionic equation when something is actually weak, don't actually write this here as just H plus. For this other one here, I wrote it as just OH minus because this one here was a strong base. Okay? H plus does still react in a 1-to-1 ratio, but that's how you do that part. For Arrhenius acids, the characteristic molecule here is an H plus. Let's have a look at what the real nature of H plus actually is. So starting off with an H atom. An H atom here would be 1 proton. Being an atom, being neutral, it has to also have 1 electron. 1 negative, 1 positive cancels out. So an H plus is an H atom that has lost an electron. And we saw that it's an oxidation process in the next chapter here. H plus is actually synonymous with a proton. So every time you've been writing H plus, you've been essentially saying this nuclear particle here, there is actually no neutrons in the most stable isotope here. It's just a proton. So that's why, especially when we got to the Bronsted-Lowry definition, we just talked about donating and accepting protons. Right? We notice a comment on size here. The H atom has suddenly shrunk very, very much because having lost that one shell, now the size of the H plus, the size of the proton, is on the order of maybe 1,000 times tinier than what I would have been before. being that really dense positive charge here makes me very unstable. So what's going to end up happening is the H plus ends up complexing with water. Fortunately for us, in solution, we actually have water in the background. Although water overall is neutral, water does have these extra electron pairs. And what can happen here is the electron pairs here can help stabilize, help spread out the H plus. It can't eliminate the H plus, that positive charge here, but in an equilibrium, it ends up forming, keep it color-coded for you here, HOH like this. And overall, we end up having a plus charge. This one here was actually H3O plus, and that was called our hydronium. This is a polyatomic like other polyatomics you've seen previous. Most polyatomics have been negative so far. This one, along with ammonium, is positive. So we've been seeing very often in this section here. Sometimes I write H plus, sometimes I write hydronium. Sure, the balancing might be a little bit different, but those two are essentially the same thing. Okay. So we have some of those definitions here as we sort of slowly work our way towards Bronsted-Lowry definitions. There are some characteristics that experimentally differentiate acids and bases. So acids tend to react with metals and produce hydrogen. That's a single replacement reaction. Litmus is an indicator. It turns acids red. They end up tasting sour. Whereas for bases, some experimental features I can find is they feel very slippery. They turn litmus blue and they taste very bitter. Those are some nice things you can compare. They did ask you early on sort of what are some common acids and some common bases here. The ones that you might want to know here is, let's say, HCl. HCl here is what our stomach uses for acid. So this is how it uses to digest the food that we eat here. Acetic acid, a very low concentration of that is actually vinegar. So if I have like 5% acetic acid, that's actually what vinegar is. Sulfuric acid is used in a lot of car batteries. Okay. Sulfuric acid is used as catalyst in many organic reactions as well. On the base side, NaOH, very common strong base here. Nicely, it's an alkali salt, so it breaks up very easily here. This one here is what they use for drain cleaner. So if you just want to memorize that here, if they give you sort of 4 bases and they say which one is commonly used for drain cleaner, just say sodium hydroxide. Ammonia sort of gave us a question mark here. We thought bases had to have an OH. Ammonia also has basic properties. Another way of saying that is alkaline properties. This one here, we actually saw we needed to use the Bronsted-Lowry definition. The Bronsted-Lowry definition is the simplified equation. As a Bronsted-Lowry base, it's supposed to accept a proton. So it's supposed to be able to grab a proton. This one here we know to be a weak base, so it's important to identify whether it's an equilibrium or one-way arrow. For the weak base, yes, the NH3 ends up becoming NH4+. But the only problem is when we started seeing the self-ionization of water, the concentration of H plus was only like 10 to the negative 7 molar. Really, really tiny. So instead, what we did is we took the simplified equation on the table. On the base side, how did we get the more complex equation? It's almost like adding OH minus on both sides. And what's going to happen is if I add OH minus, we're going to have ammonia. It is still going to be able to gain that proton, but it's not going to just steal from H plus. There's not a lot of it. It's actually going to steal from water. So water is actually going to act as an acid in this case here. Water currently has the football, and that football gets passed to ammonia. Still a equilibrium reaction. We still end up with NH4+, and it's actually the water that actually leaves behind the hydroxide. And there we go. We've formed that characteristic base molecule here. Just like Ka's were tiny, we're going to find Kb's are also tiny here. Not that the mole ratio is wrong. Every little chip on this one here that actually manages to break off, you're going to get 1 part ammonia, 1 part OH minus. It's just that the majority of it stays here. That's why on our ice tables, we can even assume so little actually breaks off, practically the whole thing is there. All right? So that's the Bronsted-Lowry definition of acids and bases. Remember, in a complex expression like this, we should have 1 acid and 1 base on both sides. The one that currently has the H plus is the acid form. The one that currently doesn't is the base form. On the other side, once the football is passed over, now the NH3 is now holding the H+. I've now formed the acid form, and the hydroxide left behind is now the base form. We've ended up forming 2 conjugate species. Conjugate pairs are things that differ by a single proton by a single H+. The acid has the proton, the base has lost it. So water and OH minus are conjugate pairs, and we have ammonia and NH4+ as conjugate pairs. So usually what we'll do here, especially when it's not clear, when you're given reactants, which one's going to be acid, which one's going to be base, we want to compare maybe their acid strengths. If both of them could be acid, they can't both donate a proton. Whoever has a bigger Ka will end up donating the proton. In this case here, it's very obvious that NH3 here is a base. But now when you actually look at both sides, now again, I have an acid on both sides. I have water that's willing to toss an H+. This is an equilibrium. The NH4+ is also willing to toss an H+ back to OH-, depending on who's stronger as an acid, NH4+ or water. I believe NH4+ is actually stronger as an acid than water is. So therefore, this one here is a stronger team. That does not mean this side is favored. It means if they do their job better, they're going to knock the equilibrium to the left-hand side. So let's just write that down here. Since the Ka for ammonium, the conjugate acid that I created, is actually stronger than the Ka for water. Water is where we get our ionization constant. It's very, very tiny. You can find these on the table. We have the stronger team on the right-hand side. So stronger team on products. We don't say that side's favored, right? Normally we say, oh, that's stronger, so that's favored. Well, no, if they do their job better, imagine this to be a volleyball game here. If the stronger team is inside, the ball is going to land more on the left-hand side of the court way more often, and therefore we use the terminology, actually, reactants are favored. And favored doesn't mean there's a stronger team. It just means that the equilibrium lies farther to the left. Equilibrium lies to the left. For this question here, they're not going to ask you what is the KEQ, but they're going to ask you just roughly speaking, is KEQ bigger than 1, less than 1 here? Knowing from our chapter 2, KEQ is supposed to be products over reactants. We have a situation where we are in equilibrium. The concentrations are constant in time. Macroscopically, nothing changes anymore. But the Ka value of the product side is bigger, so we get more reactants and less products. That fraction is going to be very tiny. We can conclude that the KEQ is actually going to be less than 1. Because there's concentrations, it can actually drop into the negatives, but at least we can say reactants are favored, which agrees with what we expected. Most of the weak base actually stays on the left-hand side. Right? That's why I make this comment. The side having the weaker acid, the losing team, is actually favored because they're going to end up having a greater concentration on the left-hand side. Okay. There were 2 organic families that were a little bit misleading, especially when you see this COOH. This is a carboxylic acid group here. We did acetic acid, let's say chaku. Every time you see that COH, it actually stands for this part. This OH here is very much the hydroxide that I would need to be a base. But turns out because this is a covalent bond, water doesn't want to break that bond. What water does here is water actually separates this H. As this H plus here ends up leaving, it drops behind a negative here. We actually end up with a little bit of resonance left over from the acetate ion that just improves the stability of that ion here. This one here, being able to release an H plus in water, actually is an acidic group. So that's why we call it a carboxylic acid. And amine already was neutral. Usually things pick up protons until they're no charge. So let's say amine here was a strong base. This is on your table. This becomes ammonia. The strong base is the NH2. That one is a one-way arrow. Turns out NH3 is itself a weak base, and it can pick up yet one more proton. This amine group here, even if I had like an amine family, let's say methylamine, this is probably the one exception. I have CH3NH2. We already were neutral. Why do I want to pick up a charge? For all these amines, they typically will have a lone pair. So like hydronium actually attacked an H+, I can end up using my lone pair and actually donate it to an H+, picking up that proton will end up converting me, in this case here, to my protonated form here, NH3+. So that's probably the one time that we end up picking up protons. We were neutral, but as I pick up that proton, I actually get a positive charge. There were chemicals that could act as acid or base. Try not to be super precise at the beginning. Don't be like, oh, it's a molecule, right? Molecules have to be neutral. Don't be like, it's an ion. Usually I use the term like, it's a species. It could be a molecule like water. It could be something. Our hint was usually you'd have an H, and usually you'd have some minus charge, because like we just mentioned, if I have a minus charge, it's probably because I had lost the proton, which would make it available to be a base. If I pick out the proton again, I can get back to neutral. So if I have an H and a negative charge here, that's another way of looking at it. So usually a polyprotic acid, having lost one proton, it would have that negative charge and it would still have an H that's willing to give up. We have other terminology here. Monoprotic means you only have one proton to give. Even if I were diprotic, 2 protons, triprotic, 3 protons like this, I always dealt with 1 proton transfers. So the balancing in this chapter was always just pretty much 1-to-1, aside from the titrations we saw later on. As we start looking at comparing the different acidic strengths and basic strengths here, we use this terminology here, strong versus weak. Be really careful. Strong and weak refer to the degree of ionization. strong things ionize 100%. These are just one-way arrows, whereas weak things, anything less than 100% is weak. They're going to end up in equilibrium, although we have some things that are relatively stronger than other weak acids. Concentration and dilute have to do with, as the name suggests here, the concentration, the amount of moles I've dissolved in the solvent. That's something else. I can have HCl that is a strong acid, but I can have 0.0001 molar HCl. Right? So strong acid, just for being the sheer nature HCl, I'm going to break up 100%, but concentration-wise, I might be very dilute. So those two things mean something different outside of our everyday, like, oh, the orange juice tastes really strong. That means concentration. Okay. The stronger the acid does its job better. It's going to be able to donate more protons. If I have a stronger base, it's going to donate more hydroxide. If I have a partner that's a stronger acid, my conjugate partner here, my Cl minus, really Cl minus here was a spectator in the hydrolysis section here, because they were 100% against, the Cl minus really has a hard time picking up that proton reform HCl. So the stronger the Ka is, we're going to find actually the weaker the Kb is of the conjugate pair. So when we compare the two different, here's me trying to be an acid, and here's me trying to be a base, when I compare my ability to be acid with my partner's ability to be a base, if I'm better as an acid, my partner is worse as a base. Which is why on our table, we had our acid-base table like this. We can read acids and bases like this. Our strong acids are going to be the ones on the really, really top left. The weak acids are a little bit lower than it here, but they also differ in strength. The stronger the acid becomes here, if I then look on the other side and look at their basic strength, look at my partner's actually ability in going backwards, the basic strength actually increases as it go down. As these acids are really good at coming forwards, my partner is not really good at coming back. As the acid is not as good as going forward, my partner is much better at coming backwards. So we're always talking in terms of conjugate pairs. Because we are in solution, we are in water, all strong acids are actually leveled by water. They're all 100% dissociated. So we actually have 6 strong acids here. Those are the top 6 there. Even though relatively we've been saying, well, the higher you are, you're actually better as an acid than anyone lower than you. In fact, all strong acids are 100% ionized. They're going to all break up 100%, and they all correspond to just a whatever molar solution of H+. So H+ is actually the strongest acid, or H3O+, that can exist in solution, because the HCl is not holding hands anymore. The HI is not holding hands anymore. Strong bases, curiously, we only actually have 2. Right? Strong bases, we're looking on the base side. We have O-2 as an oxide at one-way arrows. All the equations on the table have been simplified for you. So it's a one-way arrow, or the amine that I just mentioned. Can pick up a proton one-way arrow in forming ammonia. It's the base side. It's these chemicals here that are strong bases. It just happens to form hydroxide, happens to form ammonia. Then we cheated and we said, okay, well, since it's a base's job to, as strong things, ionize 100% and make hydroxide, what if I include in my strong base category any soluble salt that has OH? So let's say NaOH. Well, that's not on the table. Well, this is an ionic compound. When this splits apart, I'm going to get Na+. It too does a one-way arrow, like a strong thing, and it too releases the characteristic hydroxide molecule here. We're going to include any soluble salt that contains hydroxide. Pretty much compounds with hydroxide are going to be strong. OH minus, in a similar fashion here, once we end up forming the hydroxide, hydroxide is the strongest thing that can exist in solution. When we're in solution, you may have started off as NaOH, but water would have separated these two here. Basically, you're left with OH minus. OH minus itself can be a base. You're going to find OH minus on the right-hand side as well. So as a base, it can also, in equilibrium, end up reforming water. Then we started introducing in this part 1 here a little bit of the math. So make sure you know this equation, the self-ionization of water, sometimes also called the auto-ionization of water, when water is the only ingredient that actually reacts. Basically, it's water becomes H+ and OH minus. That's the simplified form. On the acidic side, how do you make this the complex form? Pretend to add water on both sides. So if I have 2 water, still this heat term, this one here is going to be in equilibrium. We're going to end up getting hydronium and OH minus, exactly the same expression. So first style of question we can do here is, well, this is an equilibrium. Let's figure out what the constant, the KEQ, is for this. Because this is for the water equation, I just redefined it KW. It should be products or reactants. It should be the H+ or hydronium times hydroxide. I don't bother dividing by water because this one here is a pure liquid. That one sort of drops out. The KW constant here gives us a nice mathematical link. Anytime you have H+, I know the KW at this temperature here, memorize this number. we did most of our chemistry at 25 degrees, the constant is 1 times 10 to the negative 14. So what's going to happen here is, even in let's say a really basic solution, I'm expecting it basically to all have OH minus inside. As long as you have water in the background, it has a really slight ability, the constant is not all that big, it has a really slight ability to end up reforming H+. So a basic solution is not one that doesn't have any acid particle. A basic solution is just one that has more hydroxide than the acid particle. Water will always self-ionize to make sure to create the other ion. None of these can be 0, because 0 times anything wouldn't be able to hit this positive constant, albeit a very tiny number. So that's sort of the first style of question here. Memorize this expression. So this one gives us a nice link between the H+ and OH-. As you steadily drop more hydroxide, sure. As the OH- increases, if these two things are going to multiply and still end up giving you the same number, we have to see that the H+ ends up dropping. So usually these are inversely related. If I have more base particle than acid particle, that's a basic solution. If they're equal, we're neutral. Sometimes they call this a pure water solution. Pure is neutral as well. Acidic means I have more hydronium than hydroxide. The other style of question they can do, why they remind you that this is actually endothermic. Let's say I just take water, and let's say I increase the temperature. This is the other style of doing it. If I increase the temperature, right, temperature was the only factor that can change the constant, then my number may not necessarily be 1 times 10 to the negative 14 anymore. We need to do our Le Chatelier here. Well, as I increase temperature, yes, the whole box actually heats up. We can track the heat term. The heat term goes up. It shifts the equilibrium to the right. What's going to happen to the amount of H+? What happens to the amount of hydroxide? Well, as I increase temperature, we can say the equilibrium shifts right, or shifts towards products. The H+ goes up, and the OH- goes up. I thought we said these two are inversely related. They're inversely related if I can assume we're at the same temperature. This time you're changing the temperature, and Le Chatelier, for every 1 mole of H+ that it creates, it's going to create 1 mole of OH-. So in some sense here, this is getting more acidic as well as more basic at the same time, because they're on a 1-to-1 ratio. As long as these two are equal to each other, they're still going to be neutral. So the next time you heat up some water, it doesn't suddenly sour like an acid or become bitter as a base. It becomes more acidic and more basic at exactly the same extent. Especially as numbers get to be very tiny, we start seeing the constants being tiny themselves. We introduce pH, POH. This P here means power of, and essentially the power of is just going to be negative log of H+. It's just redefining this H+ here. It's trying to make these numbers look a little bit nicer. So if I did negative log of H+ or negative log of OH- here, we're getting more acidic here. pH is just the name of the ruler. 7 was our dividing line. This was neutral. I do want to emphasize that's only at 25 degrees. Well, we have a situation where as I heat it up, we're actually more acidic. We're actually pushing towards the more acidic side. My pH of neutral water may be only a pH 6. Well, I thought 6 was acidic. 6 is acidic for 25 degrees, but maybe my dividing line is actually pushed over when you actually change the temperature. Only temperature can change KEQ. So the acidic side here is actually the farther away I get from 7. Let's go back to 25 degrees here. And there we get just a trick in terminology here. To get more acidic, we actually want the pH to actually decrease. Sometimes people think about, well, pH, oh, it's washing H+, it's an acid ruler. The acidity decreases? No. pH is just the name of the ruler. If this number gets smaller and smaller, farther away from 7, we're actually getting to be more acidic. As the pH increases, that's another way of saying basic. We found that the POH ruler was sort of the opposite of it. POH does truly look at the hydroxide concentration. 7, again, is the dividing line. We had derived that these two here had to add up to 14 at 25 degrees. So if I just match this up, I have a 6. If I put the 8, 9, 10 going up this way, so it's sort of like, imagine the POH ruler here as a meter stick here, just flipping it around so that when I line up my pH and my POH, these guys here always add to get 14. And again, if I'm not at 25 degrees, slightly hotter than room temperature, it's not going to add to 14, but it is going to add to the pKW, the negative log of whatever the kW is at that expression. This diagram here gives you a nice summary. We got this nice box. Pretty much anytime you get one of these, let's say I have 1 molar HCl. So I know the H+, I can use the kW expression. kW is H+ times OH-. They've done the manipulations for you here. We can actually re-express as hydroxide. Just because I re-express it doesn't suddenly make it basic. if I have an acidic solution, I still imagine I have a lot of H+. When you calculate how much water is self-ionized for hydroxide, I just expect this to be a very tiny number. If I negative log here, I get to pH. If I go 14 minus, I get to pOH. You're more than welcome to navigate around this diagram any which way. Just remember going in reverse here. There was a negative log that brought it down this way. What we're going to do in the opposite direction in words, you can say anti-log negative pH. On your calculators, it will probably be written going the other way, 10 to the minus. An exponential function here is actually the inverse, the opposite of a logarithmic function. That's why the exponent will get rid of the log for you. That was part 1 of this chapter here, introducing a lot of the definitions, a lot of the basics, and then let's just flip our way through part 2. Part 2 here involves hydrolysis. Hydrolysis here is involving a salt, really systematic procedure. You take your salt, you break it up, you cancel out any spectators. The spectator positives are anyone that's a group 1 or group 2. The spectator anions are the conjugates of strong acids. They're the top 5 strong acids. I've listed them for you here. Because a strong acid is so good, let's say perchloric acid, one-way error in forming H plus and ClO4 minus, really the ClO4 minus has no ability to go backwards. But wait, I thought there were actually 6 strong acids. Why only the top 5? It's true when we actually get to our 6th one down, H2SO4. H2SO4 here is a strong acid, but only for the first proton that it releases. So yes, HSO4 minus in exactly the same way has no ability to pick up the proton and go the other way. But being a diprotic acid to begin with, having 2 H's to begin with, we actually are going to find, oh, this has an H still to give up. HSO4 minus is actually a little bit lower on the table. HSO4 minus itself can actually act as a weak acid, so therefore this one here is not a spectator. If both of the ions are spectators, we expect the pH to be 7. The salt had no business being acidic or basic. Usually, if I have the positive ion being hydrolyzing, it's going to be acidic solution. Usually, if it's negative, it's going to be basic. So, let's just try a question here. Let's do AlF3. Okay. So, again, it's a really systematic procedure. There's no reason for this salt here to be acidic or basic. Let's dissociate the salt. Let's break up. This becomes Al plus 3, and this becomes 3F minus. Okay. We want to cancel any spectators. This time I don't have any spectators because I don't have a group 1 or group 2. F minus here is not a conjugate of strong acid. You want to look for these two on the table. Now be careful, especially for a few metals here. The aluminum ion, chromium ion, iron ion, similar to H plus not being very stable, aluminum actually ends up getting complexed. So Al plus 3 at first actually had no protons to give up. When water comes to actually surround it, water is going to point its oxygen end because the oxygen end is slightly more negative. The most common geometry is water attacks this from 6 sides, sort of left, right, up, down, even in front and behind it, a little bit harder to see. So basically an aluminum ion is actually an Al water 6. And you actually will find that on the table here. We're going to have Al H2O6. Because now it's complex with water, you can actually lose some of these H's here. As I lose an H+, you can make a prediction still weak, so it's going to be H+. We're going to end up pretty much having aluminum, but we still have 5 waters that are intact. I didn't touch those ones. For the one that I lost the H, I do have created an OH here, but I've actually released an H+, so therefore I've gone down by a charge. This one here would have been plus 3 before, so it's going to be plus 2. So this one here, as an ion, aluminum actually manages, it's only weak, so it doesn't break out very nicely, but it's going to produce a little bit H+, and it's going to make the pH a little bit acidic. If this were a titration curve, the pH would be a little bit less than 7. In contrast here, the F-, if it's the anion that actually hydrolyzes, we're going to find it on the base side of the table. So your table may look something like this. You're going to have F- and H+ in equilibrium. That's the simplified form. The complex form is F- steals from water. Yes, it forms a conjugate acid HF, but then it regenerates a little bit of hydroxide. Albeit it is still weak, so it's not going to ionize, break out very easily. Well, my final solution can't be both acidic and basic. Depending, in this case here, if both can hydrolyze, we want to compare the Ka, for this one here to be the acid, we want to compare it against the Kb of fluoride. Whichever is bigger is going to tell you which one is predominant. To find the Kb, unfortunately, all our table gives us is, it gives us a bunch of Ka constants all the way down here. It tells us how good my HF isn't coming forward. We had a nice relationship here. To find the Kb of anything, you did Kw divided by Ka of your partner. So this number here that was right beside the HF here, the Ka constant, is talking about how good HF is coming forward. If I'm F minus and I'm intending to go in reverse, I go 1e negative 14, divide by that number, and I end up getting Kb. Okay. So with that sort of background, then we can keep looking here. The acid ionization constant here, water always has a liquid designation, so that's why we always ignore it. You can write out Ka expressions, Kb expressions. Essentially, it is essentially Keq, so products divided by reactants. We ignore the water in the expression because that's always a pure liquid. Assume there's actually no ionization until you actually have a change. So when we start doing ice tables to this one here, maybe I started with just 0.50 molar F minus. I'm going to assume before it's stolen any protons, the other amounts are 0. If I'm not told anything about the bottom, I'd say minus x plus x plus x. The change line has to follow the mole ratio, and then I just do the math here. 0.5 minus x, 0 plus x is just x like that. Here, to avoid a quadratic, what we did was, because F minus has a Kb value, and the Kb, the rough numbers we're talking about is 10 to the negative 2 to 10 to the negative 10 or so, is really, really tiny. You have to write this assumption. Let's assume that when I compare how little of this that actually chips off, basically is 0.5. In some sense, we are saying the x is negligible, although we are going through this work here to figure out how small x actually is. We tested the assumption a couple times in our lessons, so it was actually a good assumption. Not only did it make the math easy, it was a proper assumption here. It's just that you do need to write down that assumption. If you actually know the change line, let's say I know the pH of the final solution, pH could give me POH. POH here could give me the hydroxide. If you actually know this number and I don't need to have x's, don't bother doing the assumption. Okay? So make sure you practice a little bit of Ka calculations, Kb calculations. Then for the last little bit of it, the main focus was the titration. Titrations were identical to what we've been seeing them at here. Titration, we want to react it until we get to something called an equivalence point. The equivalence point is when the mole ratio actually equals the mole ratio set by the stoichiometry. Another way of saying that here, especially in an acid-base equation, the moles of H plus is equal to moles of base. There's actually no excess left over. I've stopped it just perfectly so that I can end up doing a stoichiometry and mole ratio calculation. We did see sort of a spin-off to these titration questions, especially if I were polyprotic acid, if I had many protons to end up giving up. You may not have completely, let's say H3A, it's supposed to react with 3 NaOH to completely neutralize. I get Na3A and 3 waters like this. Potentially, what if when I dropped in, here's an unknown amount of A and then a moles of B, what if I only dropped in 1 mole of NaOH? What would the equation look like that for partial neutralization? So if I'm forced to balance it with a 1-to-1 ratio, sure, the H plus and the OH minus react on 1-to-1 ratio, you would definitely get a water. But you've only converted the A minus 3 here. I've only given it 1 proton here, so therefore it's going to end up being just the A minus ion. So this is going to be actually NaA, like that, okay? As opposed to getting the entire Na3A, which you should get if it fully neutralized. So partial neutralization, you just figure out sort of by mole ratio how much have you added in. We did 2 other spin-offs here. Molar mass determination, we started off making a solution. So take some solid, you make a solution, probably a larger vat of this. Then you take some aliquots, take some small samples of this here. Each of those aliquots here are titrated. And you basically find for yourself here, well, how much, let's say, unknown acid do we have in each of these containers? Well, concentration is intensive. Concentration in these aliquots is the same as the concentration in my original flask. If I can figure out the number of moles in my original flask and grams that I first dropped in, grams divided by moles will end up giving you molar mass. Or percent purity, maybe my sample at the beginning was imbued with a lot of different impurities, a lot of different chemicals. I might know the overall weight if it's impure. When I tossed it in, I'm assuming it's only the pure stuff that actually does the reaction. I can, again, backtrack here. I can figure out how many grams of this compound in my full solution was actually the chemical I was looking at. Divide out the total mass. That gives you a percent purity. Then what we did is we started looking at titrations a little bit more in the lens of a titration curve. So for a titration curve here, instead of having, let's say, phenolphthalein in there and having, oh no, it became overly pink and now I need to start over, what I did is I actually stuck a pH probe in there. And what you're going to do here, we'll just do volume of base added. The pH probe here is actually going to help me see what the pH is as the titration itself actually is performed. So if I start off, let's say I have a weak acid to begin with. Weak acids here will start off with a slightly higher pH. If 7 is the dividing line here, it probably won't be down in that region there. If this one here is a weak acid, we start a little bit higher. We do have a buffer region. There's a region where the pH is relatively held constant, even though it changes slightly. There's going to be a sort of shooting up region here. That region there, the reason why it suddenly jumps up like that, the middle of that point there is the equivalence point. You should be able to tell me why the pH is actually bigger than 7 in a weak acid strong base curve like this. It's because the salt actually hydrolyzes. The reason why it shoots up so quickly is we go from having the last remnants of H+, the one last drop of H+, through a neutral point, through equivalence, there should be no reactants, no acid or base, and then suddenly having a basic particle, OH-, signed to OH- within a very, very narrow range of pH. So a very narrow range of volume. So that all happens at VB here. We actually find out phenolphthalein as an indicator. Indicators here have a much complicated structure. It has an acid form. It's in equilibrium with its basic form here. Nice thing about an indicator is the acid form has one color. It's distinguishable from the basic form here. Phenolphthalein actually changes color a little bit too late. It changes color between maybe 8.2 to 10. It's perfect for this one because I would expect the equivalence point to be somewhat bigger than 7. We want to end up choosing an indicator that when it changes color, that's pretty close to the equivalence point. We had an acid-base indicator table. I had some other indicators that change color at pH 3, pH 4 or so. Those would still change color, but if the indicator changing color has nothing to do with the point that you're looking at, that wouldn't actually tell you anything. So we use the terminology of equivalence point or stoichiometric point for the titration. For the indicator, we actually call it the transition point. That's when the color change happens. That's when the two forms of the indicator are equal. That's when you have a combination of different colors. So for phenolphthalein, we had colorless in the acid form. We had pink in the N- form, the basic form here. So the in between of that is a sort of pale pink color. The one question that gets people here is they might ask you, can you calculate the Ka of any possible indicator here? We did the derivation. You can just memorize it for yourself. The pH at the transition point, at the middle point when it actually does change in color, the pH is actually equal to pKa. So all you would need to do is anti-log negative it, and you got back to the Ka of the chemical. Even though you have no clue what the chemical is, you know it's acid ionization constant. Remember, so for phenolphthalein as an example, 8.2 to 10, realistically it actually changes color over that range. We just divide it in two, and we say, okay, the halfway point here, I know it's on a log scale, I know this isn't perfectly half, but that's how we're going to calculate it. That's when the pH is actually equal to the pKa. For a titration problem here, we always needed to have one chemical that I knew the concentration to actually standardize something that I don't know. How did I get the very first sample? Was actually starting with what's referred to as a primary standard. A primary standard is a solid material that is very, very pure. It doesn't react with water or carbon dioxide, so that if you weigh out, let's say 1 gram of the sample here on a scale, because chemically speaking it's so pure, I'm pretty sure that the entire 1 gram is the chemical I'm talking about. For example, sodium hydroxide is not a good primary standard. You can equally well weigh out sodium hydroxide. It comes to us as little pellets here, but NaOH ends up, if you just leave it out in the air for about 10 minutes or so, you're going to find it's actually absorbed a lot of moisture from the atmosphere. You might actually have a 1 gram sample, but I know because water has actually absorbed that water, not all of this 1 gram is actually NaOH. The whole point of doing a titration is to be really, really precise. So just remember the primary standard is the solid that I start off with. We had a few acidic standard here. We called this one here KHP for short. Oxalic acid dihydrate, another really common standard. Sodium carbonate is actually baking soda. That's actually something that also keeps very pure as well. That's on the basic side. We start off with a solid. I make a solution with this one. That's going to be called the standard solution. And then I now use the standard solution, something that I know the concentration, to standardize something that I don't know the concentration of. So that's just some terminology. We did a lot of work with titration curves here. fortunately for us, we don't really need to know too much about these calculations. In the grand scheme of things, you do need to be able to analyze it like we've done here. Why is there a buffer region? Why is the equivalence point here bigger than 7? I'm going to just sort of assess, the math of it more so just on the lab. So let's say V half is going to be half of VB. That's going to be pH half, and then I have pH initial. There's an ice table, and I end up giving you these expressions for the acid side, for the base side, OH minus. For a buffer, likewise, there were a lot of calculations we did when we went over this chapter, but all they want you to know, a buffer has to be something that's weak, and you actually have to have appreciable amounts. You have to have good amounts of the conjugate base present. So easiest way to do that here is, let's start off with, let's say, a weak acid. It's a buffer's job to try to maintain the pH. And how it's going to do that, being something that's weak, it actually has an equilibrium. It actually is able to shift left or shift right. Right now, my weak acid here, it doesn't really ionize very well. If I actually add OH minus, right, the OH minus tapers off the H plus and to water, I want to shift right, great, I have a lot of acetic acid. What if I add a lot of H plus? As I add a lot of H plus, it does want to shift left, but unfortunately I run out of acetate really, really quickly. So one way of doing a buffer system, let's just add in a salt. Let's add in NaCH3COO, sodium acetate. Well, where did the sodium come from? Sodium just guarantees it's a soluble salt. This one here is going to beef up the concentration of acetic acid. Yes, that in itself will actually shift the equilibrium, but a buffer system will have good amounts of both. We like them to be equal, but they don't necessarily have to be. If I have good amounts of both, whether you add base and I want to shift right, or add acid and I want to shift left, I have good amounts of both. It's a region where the pH doesn't change dramatically when you actually add small amounts of base or small amounts of acid. For a buffer, you need to be able to block both changes, adding acid or adding base. When they later on say, what is an acidic buffer or basic buffer, they're not talking about only being able to buffer acid or only being able to buffer base. The acidic part here tells you you buffer in the less than 7 region, whereas basic means you buffer in the pH bigger than 7. We looked at a case study here in our body. So hemoglobin here in our red blood cells have this nice exchange here. Usually when the low oxygen blood here gets back to your lungs, you breathe in a bunch of oxygen. In our lungs, when the blood actually passes by there, what we're hoping is the hemoglobin will actually pick up the oxygen and actually temporarily carry it as oxyhemoglobin. The blood here has a optimum pH of something about 7.3 or so. If the pH changes drastically from 7.3, it can be very, very deadly. So we have buffer systems. We have a buffer system with CO2 bicarbonate buffer, and we actually have a nutrient buffer as a sort of phosphoric acid buffer. These ones here have good amounts of conjugates, so if you drink a pop and it's pH 2, that's not going to drop your pH all that dramatically. If you have a lot of H+, these buffer systems are going to respond to try to get rid of this change. We need from Lichitelli, it doesn't completely get rid of it. We have a problem if our blood is overly acidic, so I have a lot of H+ around here. The hemoglobin will be stuck in the form that's not bound to oxygen. The hemoglobin has trouble binding to oxygen, carrying oxygen. Or if I have a situation called alkalosis, the blood is a little bit too basic, the equilibrium is too far shifted over, no problem for the hemoglobin to pick up the oxygen, but the hemoglobin, by the time the blood actually makes its way to the different organ systems where it's supposed to release the oxygen, because it's actually bound so tightly to the hemoglobin, it actually doesn't end up releasing the oxygen. Also a problem. So naturally our bodies, in its metabolism, it maintains this nice buffer system so that our blood doesn't change really, really drastically. Last section here is just another application. This one here is just typically a multiple choice question. Which of these will form an acidic solution? Which will form a basic solution? Pretty much metal solutions will end up forming basic solutions, whereas non-metal oxides end up forming acidic solutions. Rainwater is already naturally acidic. Carbon dioxide here in the presence of water will end up creating carbonic acid. We don't call it acid rain though until the SOx and NOx will actually push the acidity actually past the 5.6 here. I'll give you an equation here. Let's say NO2 in the presence of water. This one here ends up forming HNO3 and HNO2. Sometimes it's not really easy to actually predict what it is, but all I want to show you here is because this is a covalent oxide, it's going to, almost like a fancy synthesis, it's going to create things that have H's that are willing to donate protons. So definitely acidic in solution. Okay. So hopefully that's a nice recap of the things that we learned in chapter 4. Make sure you practice through especially those ice table calculations. Thanks, guys.